Okay, welcome to ENGR ampersand 214, otherwise known as Engineering Statics in the Washington Community College System. This is the first lecture in the course series for Bellingham Technical College. So we're going to start right off with a little bit of a review of what hopefully most of you have seen in a mechanical type physics class. You're going to see a lot of the same concepts in engineering statics, but there's going to be quite a bit more mathematical rigor. So a lot of things that you might have been able to kind of wing it with a free body diagram that wasn't so complete, you're not going to be able to do here. So you're going to have to really lean on the rigorous correct way of doing things, and then you can build yourself some tools that will allow you to analyze fabulously complex structures. Okay, so let's start out with the definition of statics. What is statics? Because engineering mechanics typically includes three different disciplines: statics, dynamics, and mechanics of materials. So statics concerns itself with bodies at rest. And this means the physics definition of rest, where acceleration, here A equals 0, is always the case. So F equals, sum of the forces is always going to equal 0. It's not going to equal MA in this class because A is 0. So that really simplifies our mathematics and our analysis in almost every case. When would we use this? Anytime we don't want something to start moving or to deflect, to change its trajectory. So statics is used in a lot of civil engineering, obviously, because things like bridges and buildings, we prefer to not have them start accelerating, particularly under gravity. Okay. Acceleration, of course, is reference to an inertial reference frame. So this may be a real revisit of kinematics in physics. Obviously, we're sitting on a spinning planet that's hurtling through space. So from the point of view of the sun, none of us are at rest. We're constantly changing our direction because we're moving in a curved path around the sun. But from an inertial reference frame that's, say, the surface of the Earth. If you're building a building and you don't want it to topple over or sink into the ground, or begin to accelerate with a wind load, you would say your inertial reference frame is a point on the ground. You'd say A equals 0 in every direction, and then you could start doing an analysis of forces in all directions and make sure they sum up to 0. Okay. Which brings us kind of to Newton's second law. If acceleration, being defined by my A here, is 0, then the sum of the forces in every direction. And we're mostly going to use Cartesian. So XYZ, if you are a polar spherical coordinate fan, feel free to use phi rho theta, or r theta z if you want. But most of our problems will be set up in Cartesian coordinates. So XYZ or IJK unit vectors, which we'll do a little review of. So if we want acceleration in every direction to be 0, the sum of the forces in every direction darn well ought to be 0. And the rotational analog of that has to be true. So the sum of the moments in every different coordinate direction has to be 0. And a capital M is the symbol for moment. Now, I haven't put little arrows over the tops of all of these, but just as a reminder, acceleration, force, and moment are vector quantities. So they're going to have a magnitude and a direction. That is going to be the case of almost everything that you deal with in this course other than just mass. This is a very vector-heavy course. So everything having to do with vector algebra is totally your friend. And we'll have a couple of reviews of dot and cross product, unit vectors, what they mean, and in fact a good bit of the beginning of this course is going to be a review in vector algebra. It is a tool, can be invaluable when you're dealing with a whole lot of different forces. Makes your life easier, and it also, the biggest value in vector notation is not having to envision something geometrically that becomes just too complex and difficult. So, and you will definitely run into that. Some people are blessed and can really see the geometrical relationships. Others aren't. With vector algebra, you can get it right every time, even if you can't quite see which way things are pointed. So that's something we're all going to learn in practice. You will get problems where envisioning things geometrically just is going to be pretty much impossible. So you'll get to practice. Okay, primitives. That basically means types of units. What types of quantities are we going to be looking at? We will be looking in a lot of cases at 2D, but sometimes 3D. So we'll be looking at space, so direction and position in 3 coordinate directions, and again looking at axes defining reference frames. Again, some of the forces is 0. We're not going to accelerate in an inertial reference frame, but we're certainly going to define our position and force and moment directions in space. So a lot of 3D, mostly 2D. All works the same with vector algebra, just one more variable in all of your expressions. Time, going to get a lot of that when you take dynamics. Because nothing is accelerating, there is no time dependence in anything we work with. So looking back at the definition of acceleration as being the second time derivative of position or displacement, in some cases that's 0 by definition in statics. So d squared x, y, or z dt squared, the second derivative of x, y, or z with time is 0. That means time's not going to really matter as much to us. So you won't see a lot of time-based problems in this course, if any. Force, absolutely. That's going to be kind of one of our mainstays. And then force applied at a distance from a rotational axis. That's moment. So that rotational force analog is going to be another thing that we look at quite a bit. And we're going to look at the action of one body on another, as well as distributed kind of vector field forces like gravity on any kind of body of different shapes and mass distributions. Speaking of which, mass, even though we won't be dealing with F equals ma, because a will be 0 throughout this course, sometimes you will be given a gravitational acceleration and a mass of a body, or a distributed mass. So a body where mass is not uniformly, or density is not uniform. And so you might have to look at the force of gravity on a given body as a function of position based on its mass distribution. So we'll definitely be seeing that with distributed loads, beams, etc. Because things don't always, especially those of you working maybe in composites or other material design disciplines, will definitely be altering your mass distribution in the things that you design for lightweighting. Okay, so that's what we'll be using. Basic laws, a little physics review here. We will be leveraging Newton's laws every day, so it will become kind of natural for you. So Newton's laws of motion can either be applied to something that can be approximated as a single point or as a whole body. And we'll start with single points, but what you really need to do is get used to thinking of Newton's laws applying to bodies with distributed mass. And we'll go back and forth. Sometimes we'll find the center of mass and operate there, but when we get into the concept of moment, knowing how much of a body's mass is distributed somewhere away from its center of mass is essential to keep it from beginning to rotate. So Newton's laws of motion, particle versus body. So we'll start with particles. So what's a particle, by the way? It's something that's small enough that the velocity and acceleration are the same everywhere in the body. So it all moves together. And that means it's not going to end up rotating around any point of itself. That's the biggest implication of a particle. So how do we apply Newton's second laws to something really tiny like that we can treat like a particle? Well, we can say without external forces, the particle velocity stays constant. So that's, bodies that are at rest stay at rest unless acted upon by an external force. There you go. That's that familiar Newton's laws. Constant velocity means rest. So that means if it's stationary, it won't develop a velocity, a linear velocity in any direction, and it also means it can't travel in a curved path, because anything that is not traveling in a straight line is going to have a radial component of acceleration. You might remember from kinematics and physics. And since all components of acceleration have to be 0, with statics, nothing can travel in anything other than a straight line. So generally we'll be looking at stationary bodies, but remember, rest and the assumptions of statics apply to something traveling at a constant velocity, non-curved path. Okay. If we act on a particle with a force, we can accelerate it in the direction of the force and in proportion to the force magnitude. So that's really nice. There's a linear relationship between force and acceleration. So there's F equals ma for you right there. And that's nice that that's linear. And we can remember that from physics. And of course, because acceleration and force are both vectors, mass is not a vector, all of the direction of the force is going to translate over into acceleration. And as a caveat to that, it is the sum of the forces. So if you just have one force, that is the sum, but if you have two or three forces, the net acceleration of your particle or your center of mass of your non-particle body is going to be responding to the sum of all the forces acting on it. And that'll be a big part of what you do in this class, is sum up those forces and get the correct magnitude and direction using trigonometry. Okay. Last one, and that's the kind of the action-reaction, and this will be essential for contact forces, pins on members in a truss or different portions of a frame or of a machine working on each other. So this says that forces exerted by a pair of particles or two contact points in a body, we could extrapolate, on each other are equal in magnitude, opposite in direction, collinear on a line joining them. So you automatically know the direction of the forces on each other. So the force on A exerted by B is opposite sign of B on A, and they're in a line together. So if you know the direction of one, you know the direction of the other, and that'll be essential in solving a lot of statics problems, because you may only know one. But if you know that they're contact forces, if you know one force in its direction, you know that its opposition is pointing straight back up the other way on a line. That's what collinear means. And it'll be same magnitude pointing the other way. Okay, so that's Newton's third law. We don't deal with anything near the speed of light. We're not accelerating and we're not moving fast enough that relativity matters. So that's kind of a big relief. Mostly things are going to be stationary. Okay. As we move away from particles and to bodies, something with actual volume, where every little bit of that body may not be moving at the same velocity. So something that's rotating, for instance, or could be rotated, would fall in this category. And this is going to be most of what we work on. There's actually something called Euler's laws, which take Newton's laws of motion applied to a particle and plump them out to apply to a body with real volume. And so again, this is kind of a dive into something you may or may not have seen in physics. You may have seen things similar, but this is what we're really going to use. So if you got a finite body, like a beam or a truss or a gear with teeth, and you put it into an inertial reference frame, and in the case of a machine, it might be a single point where it's tied down or fixed to a floor, or it could be one of the axes that's rotating, anything like that. You can write Newton's laws a little bit different way. Instead of saying the sum of the forces is equal to the body's mass times the acceleration of its center of mass, we can add up momentum. That's the other way of writing Newton's second law. So we can say the result of all the external forces, could be one, could be a bunch, is going to be the time rate of change of momentum. So m times v bar. And in this case, if we're looking at the whole body, that'll be an average velocity over all the little bits of volume times its bit of mass. So this is actually an averaged and summed expression for momentum, and that's how we can apply Newton's second law for a particle in terms of momentum to something that's not a particle. It's a 3D body. Okay, so another way of saying this is the resultant moment of external forces about a fixed point equals the time derivative of the body's moment about that point. Okay, sorry, we had a bit of a pause in our recording, so we're going to go back to Euler's laws, and we're on our second element. Again, this is transforming Newton's second law and third law for particles and applying them to a body with volume, where every bit of that volume may not be traveling at the same velocity. So we can say the resultant moment of external forces about a fixed point equals the time derivative of the body's moment about that point. Okay, so basically Euler's laws allow us to account for moment, which is torque. So if you have a particle, you don't really have torque about any kind of central axis. So this is the actual physics law. I'm not going to get into it too much more because we're going to define torque mathematically and practically later on in the course, but this is the physics principle that allows us to define torque if we have a body that has volume. If you don't have volume, if you're a single particle, there won't be any torques or rotational acceleration involved because there is no r at which a force can act about an axis. You may have forces, but you don't have radius from a point. Okay, gravitation. Most of you are familiar with the idea of the force of gravity being some constants and two masses divided by the square of the radius joining them. For our purposes, we're going to assume that we are at a more or less constant radius from the Earth in its mass and the big G constant. Those will all be combined to be our metric SI 9.81 meters per second squared, or 32.2 feet per second squared English system. And if you are given a body with a mass only in pounds mass or slugs, British mass unit, or in kilograms, just be sure to multiply by gravity to get the effect of gravity on the body, maybe to find a normal force or something. Generally speaking, you'll be given a weight in newtons or pounds, so gravity acceleration will already be included. We will not be dealing with anything where the radius from the center of two bodies undergoing gravitational attraction ever matters. So nothing, no orbital mechanics or anything like that. So gravitational acceleration, when you need to use it, will be a constant. Okay, speaking of units, there's two fundamental unit systems. For most scientific work, especially mechanical engineering, you will be using the SI system, Système International, or otherwise known as the metric system. So that has standard time in seconds, which we won't use as much, length in meters, much more relevant for the course, mass in kilograms, and force in newtons. And the analogous moment would be Newton meters. You will get about maybe 30 to 50% of your problems in SI. Because statics overlaps quite a bit with civil structural, you'll see quite a few problems framed in English units, and that's simply because you need to get used to the idea of following codes and other standards which, for things most likely to use statics, still use English. Sorry, it's a fact. So the English system is going to use time in seconds as a basis. Length, the standard unit of length, is a foot. Force is pounds, so this is pounds force, for which the mass unit is a slug. Right? So mass in the English system is not pounds, it's slugs. So pound is not mass, it's force. So when you get pounds per square inch, that's force per unit area or pressure. And the general rule of significant figures. You get your first homework assignment very likely would be about significant figures. The significant figures in your answer should be limited to the lowest significant figure of your input values. And that's pretty much a constant across any kind of scientific field or engineering. And what it's basically saying is our accuracy or our understanding is limited by our inputs. So if you get some data input in feet, not tenths of a foot or hundredths, don't report your answer in newtons to the tenth. If you have one significant figure input, you get one significant figure out. Generally speaking, it's not written here in my notes, but if you're talking about decimal places, so fractions of a unit to the right of the decimal place, do not include in your final answer decimal places that are smaller, that are further right than the smallest of your inputs. So that's kind of the two-way way of limiting your significant figures in your final answer. This brings us to the idea of scientific notation. The bomb-proof way of making sure that you report appropriately both total significant figures and decimal places is to use scientific notation. And so that limits you to a single decimal place to the left, and then the number to the right reflecting your significant figures, and then a power of 10. So any of you all who are a bit rusty on using scientific notation, please refer to a good review, the Tutoring Center or Khan Academy, or any of maybe the appendices of your statics textbook. This should be pretty much second nature to you all by now, and so take a look at the homeworks. If it looks like Greek, this is a great time to brush up and review. If you don't, if you're unsure if you're reporting homeworks or on an exam, especially if you're time sensitive, in this course only, generally speaking, unless things are reported, input values reported in 3 or 4 decimal places, generally like 1 decimal place, 1 place past the decimal is usually a good guesstimate. If you're in a hurry, we're generally working in units of feet or inches or meters, so don't be reporting things out to a micron. If you are, you probably didn't stop to think of your significant figures. That's just a general rule of thumb for the general length scales that we'll be using here. Okay, that is it for our very first lecture in engineering statics, and we will continue with some definitions of force and a review of vectors and vector algebra.